Hello everyone, Mr. Tomashik here. Today I want to talk to you about precision, accuracy, and significant digits. Now, what do we mean by precision? Precision refers to the degree of exactness of a measurement. Now that's really determined by the measuring tool, alright, whether that tool is a thermometer, a ruler, graduated cylinder, anything like that, and the precision that you can get with it depends on how many lines are drawn on that device. The more lines that you have to help you with your measurement, the more precise that you'll be able to be. Everybody using that same ruler should get fairly close to the same answer with that particular measuring device. All right. Now, on the other hand, accuracy refers to how close the answer is to what it's really supposed to be. And this then is also determined by the measuring device. And for example, this ruler is 30 centimeters long. Is it really 30 centimeters long? If it is, then we say that this is an accurate ruler. So whoever made this ruler or any other measuring device, if it matches up with that, what we say is 30 centimeters or a degree Celsius or seconds like that, then it's an accurate measuring device. All right, so when it comes to measurements, we have those two things, the precision of it and the accuracy of it. And accuracy would be how close you are to what it really is supposed to be. All right, let's take a look then at what the standards are for measurement. Now, this is not something we really got to understand and learn, but originally the definition of a meter was based upon the distance from the equator to the North Pole. So that was sort of the standard that defined what a meter is. All right. Now that's not exactly the best definition because if I want to cut off a piece of wood that's a meter long, that definition is not going to be very helpful. So then we changed the definition at some point to something like this. A meter is defined as a certain number of wavelengths of an orange red light from Krypton 86. Now, we have a similar kind of thing for mass and time and so on. Now, what does that mean, wavelengths of light? Now, you've studied wavelengths in physical science, so you kind of know what that is. And a meter is actually defined in terms of something like that. Now, it's not important that we know what these things are for what our purposes are here, but know that when we say something is accurate, it means it matches up with the original definition of whatever that is that we're measuring. All right. Time is based on the ticking of a specific kind of clock. It's called an atomic clock. So a definition of a second is based on that particular device. The official timepiece for the world is a clock that's located in Switzerland. And there are other ones that are synchronized fairly well to it. One of them happens to be in Colorado Springs, Colorado. So if you want to set your watch to the official timepiece of the world, that's the clock that you're talking about. All right. So when we say something is accurate, it means that the device that we're using to measure it must match up to the agreed upon standard for whatever it is that we're measuring. All right. Now, precision, on the other hand, depends on how you build that device and how many lines you put on it. For example, when we got a ruler, there's little tiny dashes on there that can help us determine how many digits we have in our measurement. For example, here we're looking at the width of a piece of paper that somebody measured, and each one of these measurements here is more precise than the previous one. So the question is, how precise can you actually get with a standard ruler that we might have in the lab? All right. For these kind of rulers, you should come out to have 2 decimal places if you're going to call it centimeters. All right. So 2 decimal places if you call it centimeters. Now you could convert that into millimeters by moving the decimal one, but you'll still have exactly the same precision when you do that. So our rulers that we use in the lab should always come out with 2 decimal places. All right, let's look at how we arrive at this. Here's an example of a ruler kind of enlarged. And we got some arrows matched up with the ruler. And we're going to see what we would actually measure to the correct precision. All right, let's look at it a little bit closer. Here's arrow A. Now, most of you realize that these numbers represent those big dashes, and then there's some smaller dashes in between them that don't have numbers next to them. So if I'm looking where that arrow is pointed for arrow A, I'm going to say 5.2, and then the next digit is going to be an estimate in between those lines. All right, so I might look at it and say, it looks like 5.27. And where'd the 7 come from? Well, that's an estimate as to how far across that last gap the arrow is sitting on. Now, someone else might look at it and say, well, I think it's 5.26. And that would be acceptable because it's an estimate in that last column, the hundredths column in this case. So for this ruler, no matter what you measure, you should come out with 2 decimal places, and the last number, the second decimal place, is going to be an estimate, so you get a little bit of leeway when you're doing that. All right, look at arrow B. All right, arrow B, 5.9, and looks to me like it's a little bit to the left of the 6, so I'll say 5.99. 5.99. All right, someone else might look at it and say, I think 5.98, and that would be acceptable as well. All right, most people are going to look at it and say, it's a little bit to the left of 6, so probably not 6. All right, but 5.99, 5.98, maybe even 5.97, those would all be acceptable measurements, but still 2 decimal places. All right, look at arrow C, 7.52 or 7.53. All right, so that last digit, again, an estimate. And different people might come up with something a little bit different in that column, but for sure everybody should say 7.5 something, 7.5 something. All right, let's look at a couple more. All right, arrow D here, I think it looks like it's landing right on that line. So how would we report that? That's going to be 9.1, but because we always need 2 decimal places, I'm going to say 9.10. And it's important that we write down that 0. That tells us how precise we are with this particular ruler. Now, in arrow E here, it hasn't quite made it to 10.1 yet. So I'm going to write 10.07. 10.07. Now, somebody else might say, I think 10.08. And that would be acceptable as well. All right. Now, how many digits we actually get with this number is what we call significant digits or significant figures. Now, with these first few measurements here, they all had 3 digits. 2 decimal places, but 3 digits. Once I got past 10, I start to have more digits. Now I have 4 digits and 2 decimal places in the number. If I went even further and got past 100, now I'd have even more digits in the number. All right, the number of digits that are in the number are what we call significant digits. Significant digits. Now, look at the last one here, letter F. It looks like that arrow is landing right on the 11. So since this ruler can go out to 2 decimal places, we're going to report that as 11.00. And the fact that we put 0.00 just means it landed right on the line. All right, so no matter what, with this ruler, we should always have 2 decimal places. And how many digits you end up having kind of depends on how long that object is that you're actually measuring. All right, now, sometimes it's those zeros that are sort of questionable. All right, do we need to include the 0 on the end? And where the zeros count as far as the number of significant digits, that gets a little bit confusing. All right, let's look at a few rules. All right, zeros used for decimal placement are not significant. Now, what's an example? All right, here's 3 measurements. They're all the same precision. The first one is in centimeters, 2.83 centimeters. And that was made for, with a ruler like this one. All right, 2 decimal places, call it centimeters. Now remember, you can convert from any unit on the metric system by just moving the decimal. So I could take centimeters and convert it into kilometers by moving the decimal 5 places, 1, 2, 3, 4, 5, to the left. Now when I do that, I have to tack those zeros on there to show where the decimal place is, if I call it kilometers. So what that means is that those zeros are not significant digits, because the precision is still exactly the same. All right, 2.83 has 3 digits that are significant, and 0.0000283 still only has 3 significant digits. So we say that these zeros are there just for decimal placement. They're still necessary, but they're not significant digits. Now, where we're going to go with this eventually, when we do math, we have to round our answers according to how many significant digits the measurement has. So determining that is the starting point of all of this business. We'll look at the math things here in a minute. All right, now if I were to convert 2.83 centimeters into micrometers or micrometers, I would move the decimal 4 places to the right, and I'll end up with 28300. Now again, I had to add a couple of zeros so that the decimal's in the right place. Now in this case, we don't want to write the decimal there. We don't write the decimal there, but we do have to write the zeros. So we still say that this measurement has only 3 significant digits. So the precision of all 3 of these measurements is exactly the same. They're just different units. They all have 3 significant digits. And the zeros tacked on the front or on the right side are not significant digits, but still there to tell us where the decimal place is. All right, now sometimes if you have zeros to the right of a decimal and there's something in front of it, for example 2.830, that's that case where the measurement landed right on the line, and we included the 0 to indicate that. So this measurement here, 2.830, is made with a more precise ruler than the one in example number 1. All right, where we only go to 2 decimals, this ruler can go out to 3 decimal places. So it's a more precise ruler, is all that really means. Again, if I got to convert from, say, centimeters into kilometers, I could still move the decimal to the left and tack some zeros on the front, but the measurement still has 4 significant digits, and that 0 on the end counts. It just happened to land right on the line. Now, it's always about these zeros. Sometimes you get zeros that are in between non-zero numbers, like 2.05. That 0 always counts. So this measurement, we say, has 3 significant digits. All right, it hasn't quite made it to the first dash past 2 yet on that. And then again, when we move the decimal to convert to a unit, we might tack zeros onto it to get the decimal in the right place. Now, when it comes to scientific notation, this front part that is in front of the times 10 to the whatever, it shows how many significant digits the measurement has. So 2.830 has 4 significant digits. That times 10 to the 6 really doesn't have anything to do with it. That's just telling us where we would have to move the decimal if we were going to write it in non-scientific notation. So this front part, sometimes referred to as the mantissa, is going to tell us the precision of the measurement, or how many significant digits. Now, we watched that one video and they talked about this little device that you can use to help figure out if zeros are supposed to count or not. We have this map of the United States. On the left side of the United States is, or on the west side, is the Pacific Ocean. And on the right side is the Atlantic Ocean. So if I'm looking at a number that I want to determine how many significant digits there are, and I want to know, do I count these zeros or not? That's what this is trying to say. So if the number I'm looking at has a decimal present, like in the first 2 on number 1 here, they have a decimal point there. So if there is a decimal, then I'm going to come in from the left side, the Pacific Ocean side. The decimal is present for Pacific, and I don't count digits until I get to something that's not a 0. So on the first one, right away I'm going to count digit, digit, digit. But if I got the zeros there, I'm going to not count it, not count it, not count it, not count it, and then I'll go 1, 2, 3 digits, like that. So if there's a decimal point there, come in from that side and don't count anything until you get to something that's not a 0. All right, so these 2 down here both got decimals, so I come in from the left and I'll say digit, 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 4 digits. Coming in from the left here, don't count, don't count, don't count, don't count, 1, 2, 3, 4 digits. All right, like that. Now, if the decimal is absent, Then I'll come in from the Atlantic side, the right side, like the third one in number 1 here. Coming in from this side, don't count it, don't count it, and then I go digit, 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 3 significant digits. So if your number that you're looking at has a decimal point, come in from the left side. If the number does not have a decimal point, come in from the right side, and don't count anything until you get to something that is not a 0. All right, that's what that business was talking about there. All right, look at some of these measurements. All right, now 36000, no decimal. Decimal is absent. So I'm going to come in from the right side, the Atlantic Ocean side. Don't count it, don't count it, don't count it. 1, 2. That has 2 significant digits. The zeros are still there for decimal placement, but don't count as significant digits. So when I go to use this number to do math, I have to consider that it has 2 significant digits. All right, number 2, decimal is present. So come in from the Pacific side and don't count it, don't count it, don't count it, don't count it. And then 1, 2. That has 2 significant digits. Number 3, decimal is present. Coming in from the left side, I go digit, 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 3. That has 3. All right, decimal is present. Coming in from this side, digit, 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 digit. That has 4. 4800, no decimal. Decimal is absent. Come in from the Atlantic side. Don't count it, don't count it. 2 digits. All right, times 10 to the third. Don't worry about that part. Just looking at the front piece. It has a decimal point, so I'm coming in from the left or the Pacific side. And digit, digit, digit. That has 3 digits. Number 7, 25000. Decimal is present. So I'm coming in, or decimal is present. So I'm coming in from this side, the left side. I'm going to count it, count it, count it, count it. That will have 5 significant digits. Now, remember, on that ruler, if it lands right on the line, we included the zeros. This is one of those cases. All right, measurement happened to just land right on the line, and we had to write the zeros down there. All right, number 8, decimal is present. Coming in this way. Don't count it, don't count it. 1. That has 1 significant digit. All right, number 9, coming in from the right side, don't count it, and then count it, count it, count it, 3 digits. All right, number 10, that's easy, all 4 of them, because there's nothing 0. Number 11, a little bit tricky. Decimal is present, coming in from the Pacific side, don't count it, don't count it, and then I go digit, 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 digit. That'll have 5 significant digits. All right, number 12, decimal's present, come in. I'm going to count it, count it, count it, count it, count it. That, everything there, 6 digits. 13, coming in from the left, don't count it, and then I count it, count it, count it, 3 digits. No decimal coming in from this side, don't count it, and then there's only 1 significant digit. 3.6, of course, that'll just have 2. 3.6, that also has 2. 3.600, that now has 4. And the times 10 to the third not really relevant for determining significant digits. 0.00036, that doesn't count until you get to the 3 and the 6, and that has 2 digits. 30060 coming in from this side, don't count it, and then count it, count it, count it, count it, 4 digits. All right, coming in from the left side, count it, count it, count it, count it. There we'll have 4 digits. All right, now what we'll do with this is when we go to do math operations, we have to know this particular concept in order to round the answer in the right spot. All right, so here is some more. Think about what you would put for these. Give you a second. How many digits do these have? How many digits do these have? All right, try the first 5 here. All right, here's your answers. Take a look. All right, if you want to pause this video and try the rest of these, do that now, and then I'll give you the answers here. All right, here's the answers for the rest. All right. Now, being able to do this, determining how many significant digits or significant figures is the starting point for being able to round your answers in the correct spot. All right, let's look at math operations now. What do you do when you're going to do a math problem? All right, now there's a couple of different rules. One, what do you do when you add and subtract numbers? And then what do you do when you multiply and divide numbers? All right, so here's some rules. If you're going to add and subtract numbers, the first thing you got to do is all the units have to match. All right, what does that mean? All right, that means that when you have multiple measurements, they have to all measure the same thing. All right, they got to be the same unit. All right, now here's three measurements. They all measure length, so we could add them. But when you add them, you have to have the units match. All right, one of them is in millimeters, one is in meters, one is in centimeters, and they all might have a different precision. Now, if I just took a calculator and just punched those numbers in and add them all up, I'll get an answer, but it won't be anything close to the right answer. All right, so first thing I got to do is make them all be the same unit. And in metric system, that's a matter of moving the decimals. Now, it doesn't really matter what unit you make them all match up with. You can make them all millimeters or all meters or all centimeters. They just all got to be the same thing before you can add them. All right, so here's what I did here. I convert them all into centimeters. The third one already is in centimeters. All right, when I do that, it's a matter of moving the decimal. Now when I line them up, all right, remember when you do this math, you got to line that decimal up, and then you add the columns, carry the remainder, and all that kind of business, or punch it into the calculator. All right, once the units are all matched, I can punch them into the calculator. I don't have to add the columns and do the remainder and stuff. I'll just do it with the calculator, and the calculator then is going to say this. Now, here's the question. These three measurements are not all the same precision. That is, they were all done with a different ruler. Now, the question, which one's the least precise? Because then I'm going to round the answer according to that precision. The least precise one here is the one in the middle, because it only goes out to 1 decimal place. All right, if I go to 3 decimals, that's more precise, or 2 decimals is more precise. So the 0.3 or 1 decimal place is the least precise. Now, what then I have to do is round in that column. So when I added all these up, calculator would say this, but the column I have to round in is where that 7 is, because the least precise one is in the tenths column. So if I got a 7 followed by a 6, I'm going to round it up to an 8, and my final answer then would be 161.8. All right, now that is rounded to the correct precision. All right, now sometimes in 9th grade you ask the teacher, where do you want us to round the answer? And they might just say, well, round it to 2 decimal places. Well, that technically is not how you're supposed to do it. All right, you're supposed to round it according to the pieces of data that you're adding together. Now, this situation where you're going to add different precision numbers, when you're adding them, that's usually not going to happen. All right, because if you're going to measure something, you're going to do them all with the same ruler, and they'll all have the same precision. All right, but this is the rule for this, that answer cannot be any more precise than the tenths column. All right, so that's what this business is all about. All right, even though I have a couple of measurements that are more precise than this final measurement, I can't be any more precise than the least precise measurement, which is the one in the middle. All right, so that's my rule for adding. All right, take an example. Here's 3 measurements. All of them are already centimeters, so we're set to punch them into the calculator. All right, when I do that, then my calculator will say this. Now, for this, we have to round it in the correct spot. All right, this one can be a little tricky because which of these is the least precise? The answer is the middle one. All right, the middle one. It doesn't have any decimal points at all. In fact, that 0 is not a significant digit. So the precision of this number starts in the tens column in the tens column. This one is in the tenths. This one is in the hundredths. But this precision is in the tens column, which means that that 5 was an estimate. It might have been 140, it might have been 160. You get a little bit of leeway when you're using the ruler. But you had to estimate in the tens column. So then when I round this, I got to round it in the tens column, and a 7 is in the tens column. 7 followed by a 4. I'm just going to leave it as a 7, but I have to tack a 0 on there to keep that decimal in the right place. So my best answer for this problem would be 170. 170. So if I wrote down 174.51 for this unit, that's not going to be the right answer, because you have to round it in the correct spot. You got to round it in the correct spot. All right, let's look at a couple more examples. All right, look at these. I have first one is a subtraction problem, then I got an addition problem, and I got another addition problem. All right, now in number 1, they're both centimeters, so I don't need to convert units. In number 2, I got kilometers, meters, millimeters, so I'd need to convert them all to the same unit. Now here it's kind of implying that I should convert them all into meters. All right, in the third one, cc, liter, milliliter. Remember that a cc is the same thing as a milliliter, is the same thing as a centimeter cubed. So the only one I really have to convert is the liters, turn it into centimeters cubed or milliliters. All right, now what are the answers? All right, these are the correct answers. Now, what would this math look like? All right, here's the math. All right, when you do it, if you were to put this down on paper, it's going to look like this. Now you can punch it into a calculator. Number 1 had them already in centimeters, so I'm just set to punch it into the calculator and I get this. But I have to round it in the tenths column because the 0.3 tells us where we should round it. So that 0 followed by a 6 will get rounded up to a 1. That's why it's 119.1. In the second one, the least precise is the first one, and it's in the tens column. So my answer has got to be rounded in the tens column. 7 followed by a 1, I'm going to leave it as a 7. But then I got to tack a 0 on so my decimal stays in the right place. All right, so the correct answer would be 1270. For number 3, I convert them all into milliliters, which is exactly the same thing as a centimeter cubed. And then I look at the columns. This second one is precise in the hundreds column. So those zeros are not significant. So when I round, I'm going to have to round it in the hundreds column, and there's a 6 there. 6 followed by 2, I'll just leave it as a 6 and tack on a couple zeros to keep the decimal in the right place. All right, so it can get a little bit tricky adding and subtracting because of that issue. You got to get the units to match and look which one's the least precise. All right, usually we don't do a lot of adding and subtracting and worry about this. But in chemistry and physics, we do a lot of multiplying and dividing. And let's look at that rule. All right, first, if you have units like feet, pounds, kilometers, hours, that kind of thing, you got to put that with the answer. All right, so if I multiply feet times pounds, I can do that. You can multiply feet times pounds. You can't add feet in pounds, but you can multiply feet in pounds. If you take feet times pounds, you end up with a unit called a foot pound. And that is how you measure energy in the English system. All right, so math-wise, I would take 8.25 times 9.5. Now, where do I round the answer here? Now, when I'm multiplying and dividing, I'm going to round the answer to the same number of total digits, significant digits, as the factor, the piece of data, that has the least number of total digits. So now it's not the column that I'm worrying about, it's the total number of digits. All right, so looking at the numbers here, 8.25 has 3 digits. 9.5 has 2 digits. So when I round it, I'm going to have to round it to 2 digits. I don't really care where the column is. All right, now what would my calculator say? Here's the numbers that the calculator is going to say. If I take 8.25 times 9.5, calculator will say 78.375. If I take 32.0 divided by 12.00, calculator will say this. All right, 35.5 divided by 1.3, calculator will say this. Now what I got to do is round them in the correct spot. If I got 2 digits, 3 digits, and 2 digits, then this answer can only have 2 digits. So I'm going to round it to a straightaway 78. And then I'll take the foot times a pound. I'll do it like this, foot dot pound, foot pound. All right, number 2. On top, that has 3 digits. On bottom, 4 digits. So when I round this, it's got to have 3 digits. I'm going to go 1, 2, 3. This is the 6 that I need to round. All right, because that'll give me 1, 2, 3 digits. That 6 is followed by a 6, so the 6 gets rounded up, and the answer would be 2.67. All right, again, if I put down what's in blue here, I'm going to get it wrong. I got to round it in the correct spot. Round it in the correct spot. All right, look at that number 3. I got 3 digits, 2 digits, so this has to be rounded to 2 digits. All right, 2, 7, a 7, followed by a 3. We'll just keep it a 7. All right, so I'm going to write 27. Now, in this case, I don't want to put a decimal point there. Actually, if I did, I'd still be okay. But I can't round it to 27.3. That would be too precise. And I don't know it to that precision. I can only have 2 digits in the answer. Now, it may or may not even have a decimal point. In this case, it won't have a decimal point. And if I take kilometers divided by hours, then I get kilometers per hour. All right. Feet divided by seconds, I get feet per second. All right. Those are both velocities or speed measurements. All right. That's what we mean by rounding after a math operation. All right. Your calculator will tell you one thing, and then you have to round it in the correct spot based on the numbers that you're actually multiplying. All right, here, let's look at one more example, and then we're going to stop on this. All right, I got 125 kilometers multiplied times miles per kilometer. That's kind of like a conversion into miles, really. And I'm going to do 125 times 0.6214, and then I got to round the answer. All right, then I got to round the answer. Now, what would my calculator say? All right, here's the numbers that the calculator is going to say. All right, so 125 times 0.6214, calculator will say this. Where should I round it? 125 has 3 digits. 0.6214 has 4 digits. So I got to round this to 3 digits. All right, the third digit is the 6, followed by a 7. I'm going to round it up. So the correct answer would be 77.7. All right, where am I going to round all the rest of these? Number 2, I got 2 digits, 3 digits, round the answer to 2 digits. Number 3, all right, I got this 1/2 out in front here. Notice there's no digits behind her, no units. It's like a pure number. So that's really not going to play into where I got to round it, because that's like a perfect 1/2. All right, the 50 kilograms and the 8.05 meter per second squared, those are measurements done with some kind of measuring tool. So I'm going to round it to those things and don't worry about this. Even though when I multiply 1 times 50 times that divided by 2, this is what the calculator says. 50.00 has 4 digits. 8.05 has 3 digits. Therefore, I got to round the answer to 3 digits. All right, a 1 followed by 2, I'll just leave it a 1. Don't put a decimal point. Number 4, I got 5 digits divided by 3 digits. Round this to 3 digits. 11.3. Number 5, 2 digits. That 0, remember, doesn't count. All right, it's still there to tell you where the decimal is, but only has 2 digits, 4 digits. So when I round this, I got to round it to 2 digits. All right. That's rounding it in the correct spot based on the data that you use to do the calculation. All right, and that's how you deal with significant digits when you do calculations. It's kind of 2 different rules: what you do when you add and subtract, and what you do when you multiply and divide. All right, so that's significant digits.